In this video, we're going to look at Newton's second law and how we can define it based on how impulse changes an object's momentum, either speeding it up or slowing it down. So let's start by looking at Newton's official definition of this second law. He said that the rate of change in momentum in a body is directly proportional to the unbalanced force acting on that body and takes place in the same direction. Now, it's kind of a mouthful, so let's break it down and really turn it into an equation for us. First, let's look at this rate of change of momentum. Anytime you have a rate, or rate of change, you're going to be dividing it by a change in time. So we'll take a delta p, change in momentum, divided by delta t, change in time. That is proportional to an unbalanced force. So this is not equilibrium. This is not all the forces canceling each other out. That was Newton's first law, a law of inertia. Object remains doing whatever it's doing if there isn't an unbalanced force. Here we have an unbalanced force changing this momentum. This force we're just going to define as F. But really later on, we'll be thinking that more of the net force rather than just any specific force. It's the overall unbalanced force that's acting. We're going to return to this equation and expand it out a little bit more. But before we can do that, let's first define a couple more physics quantities. Velocity, we've seen already, is a change in position over time. We've also defined it as basically speed with direction. So it is how fast you are moving. So speed with direction, but also which direction you're going. So it could be positive or negative. Acceleration is just an object's change in velocity over time. And since velocity is part of this, it means that we need to understand the definition of velocity to know if the acceleration is changing. There's actually three different forms of acceleration if you dig into it. One is the type of acceleration that we all imagine. It's speeding up. If you're speeding up, you are changing your velocity. But you're also changing your velocity if you're slowing down. Oftentimes people call this decelerating, but it still falls under the physics umbrella in the world of acceleration. Speeding up, slowing down, those are both changing an object's speed, and velocity is speed with direction, so that's changing velocity. The third type of acceleration is looking at that second half of the velocity definition, and that is changing direction. So you could be going around a curve, maintaining the same speed of 30 meters per second, and still be accelerating because you are changing your direction constantly. We're going to save that one for when we get into circular motion. In this unit, we're going to look primarily at this speeding up and slowing down, and we can define that acceleration um, with that idea. We can also put a number to this. If we go back to graphing, if I had a graph of something that is changing its position like this, I can see every second it moves a little bit farther than it did the second before, which means its meters per second keeps increasing as you're going. If I map that on my velocity versus time, I'll see that it starts around 0 and ends around 2 meters per second in a time of 7 seconds. I can find the slope of that and basically say 2 meters per second divided by 7 seconds, and we'll get around 0.29 meters per second per second. Or in physics, we often combine that and say meters per second squared. Or in IB physics, you might see that as ms to the minus 2. This is a number to basically say, here's how fast we're getting faster. We can also calculate this idea without a graph. Here's the official equation defining acceleration. It's your change in velocity over time. So your final velocity minus initial velocity divided by the change in time. For acceleration, we'll use a lowercase a. Final velocity is a lowercase v, and then you'll notice initial velocity is a lowercase u. We'll see that again later on. Change in time, we're just going to use a t to represent the time that elapses between your initial and final velocity. If I look at units, I've got my change in velocity will give me meters per second, and my time will give me seconds. So if I take meters per second divided by seconds, there's our meters per second squared again. So acceleration, whenever we see it, is typically going to be meters per second squared as our way of defining it. Now let's think a little bit more about that unit. You might see it any of these three ways. I want you to be able to conceptually understand meters per second squared in the same way that you can understand meters per second. If I said I'm moving at 5 meters per second, it's not too big of a leap to say, well, every second I move 5 meters. Meters per second squared is the same idea. It just means every second you're moving so many meters per second faster. So think of it rather than meters per second squared. When you're thinking about acceleration, imagine it as how many meters per second faster or slower I'm traveling every second. It's meters per second per second. So if I'm going 5 meters per second, every second that I'm traveling, I am speeding up and gaining another 5 meters per second in my velocity. which means I could be starting at 0, and then 1 second later, I'm at 5 meters per second. And then my speedometer is at 10 meters per second, then 15, and I'm getting faster and faster as I go. We can see this in an equation looking at some actual numbers. What's the acceleration of a car that accelerates from 15 to 35 meters per second in 10 seconds? We can start by listing what I know. I know that the goal here is I'm trying to find acceleration. I know that the initial velocity u is 15 meters per second, the final velocity is 35, and the time is 10 seconds. If this is my equation, I just plug it in. So the final minus the initial, 35 minus 15, divided by 10. 35 minus 15 is 20, divided by 10 is 2 meters per second squared, or 2 meters per second per second. So if I started at 15 meters per second, every second I gain another 2 meters per second to that speed. I'm going even faster than I was. And then after 10 seconds, I finally arrived at my top speed of 35 meters per second. All right, let's look at another example. Find the average acceleration of a northbound train that slows down from 12 meters per second to a complete stop in 8 seconds. All right, I'm trying to find acceleration again. I know that my initial velocity u is 12 meters per second. In this case, my final velocity, it's not given as a number, but it says a complete stop. So I know that it comes to 0. And then my time is 8 seconds. Again, my equation is final minus initial. Here my final is 0, my initial is 12. So I'm actually going to plug it in as 0 minus 12 over 8. It means I'm going to get a negative value of negative 1.5 meters per second squared. Acceleration, like velocity, like momentum, like force, is a vector quantity. Acceleration has a direction to it, which means it could be negative, and in this case it is. So what does that negative mean? Well, in this case, you might look at it and say, well, the thing that's different is this one slowing down and the other one was speeding up. That is partially true, but it's not an always kind of rule. So let's look at the official rule to know if something's speeding up or slowing down and what a negative is going to mean. If you have an acceleration that's in the same direction as your velocity of the object, so say you are moving to the right and your acceleration is also to the right, let's call them both positive, that's going to result in you speeding up. If you are moving to the left, a negative acceleration, and then you apply a negative or a negative velocity and you apply a negative acceleration, that's like you're speeding up to the left, you're becoming more negative. If this is the case, we think of the net force going with the motion. Imagine a little dude pushing you from behind and then causing you to get faster in whatever direction you are going. We're going to say that the object is speeding up. If the acceleration is in the opposite direction, so you're trying to go negative, but your acceleration is positive, it's kind of like a little dude is pushing from the front, pushing you against the direction that you're traveling. Or if your velocity is positive and your acceleration is negative, that will cause you to slow down as well. So that means you're going to slow down because your net force is opposing the motion. So the tricky thing there is it means that acceleration could be negative to give you slowing down, but a negative acceleration could also mean speeding up if you happen to be moving in the negative velocity already. So you're gonna have to pay attention to which way are you moving to know if that negative acceleration is actually speeding or slowing. All right, so both of these descriptions are talking about a net force. So let's connect net force back into acceleration. Remember this equation that we derived earlier from this official writing of Newton's second law? We said that the change in momentum is divided by the change in time, and that's equal to some unbalanced force. Well, a change in momentum is just your final momentum minus the initial. If we know that v is final and u is initial for velocities, and momentum is just mass times velocity, I got mv minus mu to give me a change in momentum divided by the time. I can pull mass out of that and see that the mass times v minus u over t is the same thing. We've seen that before. V minus u over t, that's acceleration. So I can say F is equal to the mass times the acceleration. That might be a definition of Newton's second law that you're more familiar with seeing. But I want you to know that the official definition is actually based on changing momentum. It is a force causing the momentum to change, not necessarily a force giving you acceleration. It works out the same way, but you should be comfortable with both ideas. All right, that equation shows up in the IB Physics data booklet in A2. Here it is in both forms, MA and delta P over delta T. So, what does that mean for us? It means that if an object is in equilibrium, so there is no net force, all the forces cancel out, then the object is not accelerating. It can't be if F equals ma. No acceleration could mean one of two things. It could mean that it's not moving. That is what we are most comfortable with thinking of, that an object in equilibrium, of course, is not moving. But it could also mean that it's not accelerating, just constant velocity. And the reality is, both of these are constant velocity. Not moving is just constant zero. Constant velocity captures in all the other possibilities that you are cruise controlling down the highway. The force of your engine perfectly counteracts the force of friction, and you are not speeding up or slowing down or going in a straight line at an acceleration of zero. Okay, the other side of this means that if there is a net force, if the forces don't cancel each other out, there will be an acceleration. In this case, since force is equal to mass times acceleration, rearranging for acceleration, the acceleration is equal to force divided by the mass. Now that means a couple things. It means that if you double your force but you keep the mass the same, you're pushing twice as hard on the same object, it's going to accelerate twice as fast. If I keep the force the same, but I double the mass, that more massive object is going to be more sluggish and changing, and the acceleration is going to be less. It'll be half as much. But if I double the force, so twice as much force on twice as much mass, those factors are going to cancel each other out, and you're going to end up accelerating the same amount as if you had half the mass and half the force. So let's look at a couple examples with this and see how all of this connects with the stuff that we've already been seeing with forces. How fast is this 100 kilogram block accelerating? Now we know that the force is equal to mass times acceleration, so we can find acceleration from that. But the problem is that implies one force. There are four forces that are acting on this object. So when we see F equals ma, really what you should be thinking is F net, the net force, is equal to mass times acceleration. It's a net force that's unbalanced force that causes a change. So let's find a net force. I've got 600 newtons going up, 200 newtons going down, which means overall in the vertical direction is 400 up, 400 to the right, 100 to the left. Overall, we've got 300 to the right. Now, to combine these, it's not as simple as just adding them or subtracting them. They are at right angles to each other, which means the actual net force is at some angle that's going through there. I can create a triangle basically by sliding this over and finding a hypotenuse. This is a 3, 4, 5, or 300, 400, 500 triangle. So I can use that 500 newtons as my net force, which means overall, it's like this object is receiving one force that's 500 newtons. So if I know the acceleration is equal to force divided by the mass, that force that I'm going to use is 500 newtons divided by a mass of 100 kilograms. Give me 5 meters per second squared. So if you have more than one force, combine them to make a single force that you can then use later on. All right, let's look at a more complicated problem here. Let's look at a scenario where we're trying to find the net force for an 8 kilogram object being pulled with a force of 40 newtons at an angle of 30 degrees to the surface, where mu, the dynamic friction in this case, is 0.25. What's the acceleration of the block? Now, this picture is not fully complete. There are some other forces that are acting besides this tension force at an angle and a force of friction opposing the slide. We know that if we can combine all these forces, a net force is equal to mass times acceleration. So the acceleration that I'm looking for is the force, net force, divided by the mass. I know that there's a force of gravity. This object has mass. So let's start there. Fg is equal to mass times gravity. The mass is 8, the gravity is 9.8. So my force of gravity is 78.4. If this object is sitting on a table, I also know that there's a normal force pushing up. There's another way that I know that there's going to be a normal force is there will be a force of friction for this object sliding, and there can't be friction unless there's contact with the surface. So we have that clue in there as well. I can't just assume that the normal force is equal to the force of gravity in this case, because this tension force is pulling up a little bit. So if Fn were the same as 78.4, this Ft would put it out of equilibrium, at least in the vertical positioning, and that is not going to happen if this object is sliding horizontally. So let's first make this Ft into a triangle and figure out how much up and how much over we are actually talking. The how much up question, this is my opposite side, so it's 40, Ft, times the sine of 30 degrees. I can calculate that. That ends up being 20 newtons. So now I actually know a little bit more information about the verticals. I know that going down, I've got 78.4 newtons of force, and going up, I've got Fn and 20. That should add up to the same thing as Fg, because in the vertical direction, we are not accelerating up or down. We expect that to be in equilibrium, so the only net force is going to be horizontal, causing that acceleration, which means F net is just going to be the difference. It's 78.4 minus 20, or 58.4. Get my last unmarked force here. Ff we know is equal to mu times Fn. That's my equation for force of friction. Mu is 0.25, and Fn we actually just calculated is 58.4. I can solve for that. That's 14.6. Now I'm close. I have almost all the forces that are factored in here. This Ff is perfectly opposite Ft in the horizontal direction. So let's find how much horizontally Ft is pulling. 40 times the cosine of 30 is 34.6 newtons, which means really what we're looking at is this picture here. We can kind of ignore that diagonal and say, well, it's not really there. It's just 20 up and 34.6 over. So let's redraw this as something that's a little friendlier. It's basically this, that you have 78.4, that's your weight going down. The orange is that tension force is at an angle, so 20 up, 34.6 over. The normal force is 58.4, and the force of friction is 14.6. Now I can see the verticals, they cancel each other out. So the only thing that I'm going to actually really care about to find a net force, these two. Well, 34.6 minus 14.6 gives me an acceleration equal to a net force of 20 newtons. That's the difference between these horizontals. Divided by my mass is still 8. It feels like a long time ago. But I can calculate now that my acceleration is 2.5 meters per second squared. Wow, there's a lot of information in there. There's a lot that you have to do. Understanding this free body diagram, doing some angles, drawing a picture to find Fn, using an equation to find Ff, finding a net force, and then using that net force to find an acceleration. There's a lot in that problem, but that's a great problem to see how all of this can fit together. Let's look at one last example. This example is going to stretch for a few slides as we see it in different ways. We're going to start by making it as simple as possible and just say, what is the acceleration of this 10-kilogram block? There are 4 forces. We know that the net force is equal to mass times acceleration, so I have to find the net force. I can see pretty quickly, even though it's tilted and looks a little scarier, this 75.1 cancels out going up and going down, at least at those angles, which means I'm left with just 2 forces that are opposite each other. The net force is the difference between the two. It's 51.7 because that's 63.0 minus 11.3. If I know that, I know the acceleration rearranging my F equals ma. Acceleration is F net divided by m. 51.7 divided by the 10 kilograms gives me an acceleration of 5.17 meters per second squared. Okay, we're going to see how this plays in just a little bit. First, we need to remember a little bit about what we're going to do with ramps and what we've seen with ramps already. You will remember that if you place something on a surface, that surface is not perfectly horizontal, gravity doesn't care. Your weight is still going to go straight down to the center of the earth, irrespective of like what your surface actually looks like. So something that's going to be helpful for us problem solving is to split that up into components that are parallel and perpendicular to the ramp. So down the ramp and then normal to the ramp into the ramp. Now that perpendicular force is going to be perfectly opposite to the normal force because normal is always perpendicular to the surface. And I do not expect that this object is going to be accelerating up out of the ramp or into the ramp, melting into that surface. So I am going to say that these two will always be equal. We expect that to always be the case. The only thing that would change that is if you had some tension force that was not perfectly horizontal or perfectly parallel to this ramp, that might give you some components that are going to change it. But most of the time, we're going to see those being equal. Now that leaves us with the friction force. Friction force is opposing motion. We're going to assume that this object is sliding down the ramp. But if it were sliding up the ramp, it's possible that friction force could be going down. Now, before, when this was in equilibrium, we said that friction force is equal to the parallel force. But that's not always going to be true. You won't always be in equilibrium. What we know to always be true is the force of friction will always be equal to mu times Fn, the coefficient of friction times this normal force of the surface pushing on it. So let's take that and actually do a ramp problem here. We've got an object that has a mass of 10 kilograms. It's on a ramp that's 40 degrees. Mu, it's a little hard to see there, is 0.15. So I'm going to calculate all the things. First, the force of gravity is equal to mass times gravity. It's 10 times 9.8 or 98 newtons. That's going straight down. But I can split that up into my components, basically making this triangle here. It's a right triangle with a 40-degree angle that matches my ramp, which means my perpendicular component, this pink one, is attached to the angle. So we'll say it's FG times the cosine of theta, or 98 times the cosine of 40. That's 75.1. Parallel force is going to be FG times the sine of theta. That's the opposite of my angle. 98 times cosine or sine of 40 is 63.0. You'll see that there. Okay, now we can solve our other things. We said that Fn is always equal to the perpendicular force, 75.1 Fn. We know that the force of friction is going to be counteracting the motion. If this object is sliding down the ramp, we're going to say that it's pushing up the ramp. And that force of friction, in this case, is not going to be equal to the parallel force, but we do know it to always be equal to mu times Fn. I know what mu is. That's 0.15. That's given in the problem. Fn I just found was 75.1 because that was opposite the perpendicular. So I get force of friction to be 11.3. So now that we've seen all of these forces and where they're coming from, that picture might actually look familiar. Now we see four forces that are acting on an object and we need to find a net force. You've seen that already. That was the example problem that we started with, and we were pretty easily able to determine that the net force was 51.7 and our acceleration was 5.17. So now going back to this example, we see that the net force is just the difference between those two, 51.7, and the acceleration is the force divided by the mass of 5.17. This is another really intense example. There are a lot of pieces to this and a lot of things that you need to understand about how forces interact, especially on a ramp, to be able to get all the way from where we started to where we're ending here at 5.17. The key is being able to turn the initial picture into this picture where you've got your four forces that are all perfectly opposite each other so you can easily find what the net force and then ultimately the acceleration is going to be. So what have we seen in this video? Well, there are a lot of different pieces. You should be able to define and calculate the acceleration in terms of velocity. And then we use that to describe Newton's second law in terms of momentum, and then ultimately acceleration. We can calculate the force with mass and acceleration, and calculate acceleration with force and mass. And then all of these other pieces, you should be able to calculate the acceleration of an object experiencing weight, normal force and friction, calculate the acceleration if you have an angle and friction and a ramp, and then the connection between constant velocity and balanced forces, and how we're going to see that happening sometimes, whereas sometimes it's going to be this net force causing an acceleration and making it change.